Okay, we will resume our lecture here. So we ended at the space temperature control only for CAV system under partial and full load conditions. Now we'll be moving on to single zone control for CAV system. So single zone control stands for one control loop for two zones. As illustrated in this schematic here, we have zone number 1, zone number 2. And the two zones might have different SHR ratio. However, only one zone is connected with a thermostat, and the thermostats will further control the flow rate of the coil. So this is how the single zone control looks like for on a psychrometric chart. So you can see that we have R1 return air for zone 1, R2 return air states for zone 2, and since the supply air temperature and supply air humidity ratio remain the same for the two zones, the only difference here between these two zones is their SHR ratio. So you can see that the SHR lines are different for the two zones. So from this schematic, zone 1 has a thermostat. So obviously, temperature for zone 1 is under control, and temperature for zone 2 is remained uncontrolled. So temperature zone 2 might be too cold or too hot. So that means for different zones, you will need to control individual zones, use individual zone control. And this is consistent with what we have learned in zoning. So in zoning, we learned that the for a single zone, it will be controlled by a thermostat. So in this case, zone 2 will also need to be installed by the thermostat, by one thermostat. The third control strategy we will learn for the CAV system is terminal reheat. So you can see that here we have two zones, and for each zone is installed with a thermostat, and the thermostat is connected to a reheat coil. So for this CAV system, all the CAV system will first of all share a air handling unit. So for the air handling units, for different zones, their supply air right after, or the air conditioning right after the air handling unit will remain the same. However, for their different zones, in order to realize individual zone control, the required supply temperature here for different zones might not be the same. So this is where reheat coil comes to play. So we can see that the temperature sensor is connected to the reheat coils, and based on the requirements of the individual zone, the overall or the primary air right after the air handling unit can be treated to a relatively lower temperature, and then the actual temperature, the actual supply temperature, supply air condition can be controlled by the individual reheat coil. So this is the characteristics of the terminal reheat. First of all, the cool air is at a preset supply temperature. So the preset supply temperature means here. You can see that supply temperature is typically 13 degrees from this primary air handling unit, or as here it says, central air handling unit, provided to various zones. And the reheat is provided at the conditioned space for individual conditioned space. And it's capable of maintaining a space temperature, and it can passively maintain relative humidity within a small range for at full load and partial load. And the supply air temperature is controlled, and if the space latent load at partial load equals the latent load at full load, and then the room state point will remain unchanged. So this is how it looks like for terminal reheat. So you can see that the central air conditioning, or the off coil, sorry, the off coil air conditioning air states remain the same. So from state M to state C up to state S is the air conditioning process for the air handling unit. And for full load condition, we have this room ratio line. And S prime is the partial load condition. And when it's at the partial load condition, the supply air from the central air handling unit will first go through a reheater from S to S prime here. And we can see that the humidity ratio for, say, S and S prime will remain the same, as the terminal reheat here will provide sensible heating process. And the space latent load and the partial load remain the same, so the humidity ratio of the return air will remain the same. However, if the room ratio line remain the same for the partial load condition, then from the psychrometric chart, we will see that the relative humidity of the partial load condition will be lower than the relative humidity for the space for the design condition or full load condition. So for the characteristics and summary of terminal reheat, first of all, the air goes through cooling, and then it goes through heating. So there will be some part of the energy wasted. And this is the reason why the terminal reheat is only recommended in the following scenarios. First of all, if we need to provide close control of space, relative humidity, and temperature, and we can use recovered energy to provide for terminal reheat, or we will need to prevent space relative humidity from rising above 65%, or to prevent condensation to occur at the outlets. So that's for the terminal reheat. Another control strategy for a CAV system is bypass control. So you can see that for bypass control, since the CAV system operates at a constant air volume, then if the room temperature is not needed to be maintained at a very low temperature, and the supply air volumetric flow rate is higher than the needed value, then part of the supply air can be bypassed. So this is the return air, and we have a return air mixed with the conditioned air, and in this way, the conditioned air temperature or supplied air temperature, actual supply air temperature can be lowered. And this is how it looks like on the bypass control. So you can see that for the design condition, we have return air mixed with the outside air, and the mixed air will go through the cooling coil, and then it will follow the space room ratio line to reach to the return to the condition, to the design state. However, if we have partial load with bypass airstream, the outside air will remain the same. And then for the actual for the actual supply air, it will be mixed with the point B here. Point B here is the air state right after the cooling coil. So for point B, right after the cooling coil, it will be mixed with, part of it will be mixed with the return air, and B prime is here actually, or S. B prime is here. So in this way, the system can work under partial load condition. And for this psychrometric diagram, the fan heat is neglected. So this is the, let me see, this is the last control strategy of the CAV system, and it's called temperature and high limit humidity control. So you can see that for the return air, we have two sensors. We have a temperature sensor and we have a humidity sensor. And both of them is connected to a controller, and the controller will further control the chilled water flow rate at the cooling coil, and the hot water flow rate at the heating coil. So when the indoor humidity level rises beyond the high limit, then the humidity sensor signal will become the stronger signal. And if the humidity sensor signal becomes the stronger signal, then in order to decrease the humidity ratio, we have to further increase the cooling load at the cooling coil. And when we further increase the cooling load at the cooling coil, it will be overcooled. The air will be overcooled here. And this is how the heating coil comes to play. So when the air goes through a overcooled cooling coil, first of all, the humidity ratio will be treated to the design value or the preferred value. And then at the current scenario, the temperature is overcooled. And this is why we will need an extra heating coil here. So in this scenario, temperature and high limit humidity control, the waste of energy is inevitable. So the waste of energy will exist, and the reason is that to dehumidify the moist air, cooling coil is the only method that can be applied for this system. So there are other systems, but other HVAC systems is, the principles is not the same as our traditional HVAC system. And we will introduce that in HVAC in part 2 of this subject, 3226, in next semester. Okay, so the previous slides are on the CAV system illustration and CAV system control strategies. So we have introduced several control strategy of the CAV system. And now we will be moving on to fan coil system. So this is how the fan coil system looks like, and it's mainly installed, and it's very prevalently used in office buildings. So each individual room will be equipped with one fan coil unit, and we can think of it as a mini air handling unit. So this is how it looks like for a small one and a larger fan coil unit. Okay, so this is a schematic of a fan coil unit. So you can see that it has the inlet and an outlet is here. So the inlet air will be introduced to a heating coil or cooling coil, and we have a supply air supplied right into the room. So the fan coil unit will be mounted or will be installed in each individual room. And it's basically a small CAV. So the return air, outside air, and the heating coil, cooling coil, all the major components can be, all of the major components can be found inside a small fan coil unit. And normally the fan will be at least a 3-speed fan. So it's actually, we cannot actually say that it's a small CAV system, but it's actually a small VAV system, as we have variable speed fans here. Okay, so the fan coil unit is standard size, and it's based on airflow capacity, and the standard size can is ranged from 100 to 600 liter per second, or 200, 300, 400, up until 1,000 and 200 cubic feet per minute, or CFM. This picture illustrates a typical fan coil system. So you can see that this is one room, and we have fresh air intake and return air. And the temperature sensor is connected to a controller that directly controls the chilled water supply and return. And the chilled water supply and return is connected to a major chiller. And that chiller will provide chilled water for all of the fan coil units. And therefore, the central chiller outlet air temperature will remain constant. So the controller here will only control the mass flow rate of the chilled water. And at the fan coil unit, at the chiller here, we have a condensate drain pipe. And in cooling condition, the chilled water will, or the coil here will serve as a cooling coil. So inevitably there will be water condensate. So this is the reason why condensate drain pipe is needed. And then the mixed air, when it goes through the cooling coil, it will be supplied back to the room. And that is for the typical fan coil system and control strategy. Okay, for the control, here is a close-up of the control module here. So for the thermostat and fan speed selector, you can obviously selecting different fan speed, and different fan speed is corresponding with a different airflow rate. And the thermostat and fan speed selector will also control the control valve here. And this control valve is a motorized on-off control valve. So the room temperature fluctuation will exist if we use this on-off control valve. For example, we have an off setting, so set point and the on setting. And the set point is our preferred room temperature, for example, 24 degrees. And off setting could be 0.5 Kelvin or 1 Kelvin below the set point, and on setting point can also be 0.5 or 1 Kelvin above the set point. So when the temperature falls below the off setting, then our system will be turned off, or the chilled water supply valve will be turned off. Okay, when it's turned off, the temperature of inside the room will rise up. And it will rise up until it passes the on-setting temperature. And when it hits the on-setting temperature, then the control valve will be turned on. When the control valve is turned on, the room temperature will start to decrease up until it reaches the off setting, where the system will, or the control valve will be turned off again. So you can see that even if we have a set point to a room for this kind of fan coil control strategy, the room temperature will fluctuate, and the system will go through on period and off period periodically here. And the control differential is the offsetting and on-setting temperature difference. So this is the control for fan coil system. Instead of this kind of on-off control, we can also install a duct heater inside the supply air duct for fan coil unit. So the duct heater will serve as a terminal reheater, similarly to the terminal heater in CAV system. So fan coil system can be classified depending on how fresh air is supplied. normally it can be categorized into space and ventilation fan coil system or primary air fan coil system. For space ventilation fan coil system, it's actually as illustrated in our previous slide. We have fresh air intake at the local inlet, or right here we have this local fresh air intake. So we have fresh air intake at local fresh air intake, and then we have return air mixed with the fresh air. And all the control strategy and schematic of the system remain the same as for compared with our previous slide. Okay, so this is how the fan coil space ventilation fan coil system looks like on a psychrometric chart for summer cooling condition and winter heating condition. Okay, so for summer cooling condition, we have this outside air with the return air mixed. Okay, outside air, fresh air mixed with the return air. And it will go through the coil, and that will be supplied back to, right after the coil, it's supplied back to the room here. Let me see. Okay, and for the winter condition, the outside air first mixed with the return air, and it will go through the heating. And this state M to state F represents the mixed air first goes through the fan. So we have a, if we consider the temperature rise due to the fan power, then there will be a very small temperature rise across the fan. So we have mixed air with a little bit of the temperature rise due to the fan power, and then goes through the coil. And here it's similar. So the major difference between the space ventilation for fan coil system on psychrometric chart is between this scenario and the CAV system is the mixed air will first go through the coil, and then it will the fan temperature rise due to fan power will come to play for CAV system. And for fan coil system, the mixed air will first go through the fan. Okay, and the second type of a fan coil system is primary air fan coil system. So you can see that it has a primary air handling unit here. And for the primary air handling unit, for example, for this building, it will have a fresh air intake for the central or for the primary air handling unit. And for the primary air handling unit, the layout is similar to the CAV system, as you can see here. It will go through the filter, coil, and the fan. And then after the after the primary air handling unit, the air will be supplied to each of the individual fan coil unit outlet. Okay, so at this individual fan coil unit outlet, the preconditioned primary air will first of all mix with the return air. So this is the primary air, and this PA is correspondence with the moist air condition here. And then the mixed air will be treated to design space humidity. It will go through the fan first of all, and then let me see, state M. Outside air, return air outside, and then it will be treated to the space air humidity. As listed here, we have this supply and return. Okay. So another design condition is another control strategy for the primary air fan coil system is, first of all, the preconditioned primary air mixed with the return air, like here, preconditioned primary air, PA, mixed with the return air here, and then it's treated to low humidity to handle all the latent load. So then it will be treated as to the low humidity as here supply, and then it will follow the SR line. Compared with here, we have this return air and primary air mixed here, and then it will pass through a wet cooling coil, like here. And for here, we can see that the primary air is already at a very low relative humidity. A very low humidity ratio. So this is our required or design humidity ratio, and we can see that the humidity ratio of the pre-treat primary air is very low, whereas here for our required humidity ratio, the primary air is only treated similar to that range. So if this is the case, and then the mixed air will go through a wet coil to handle the space latent load. Whereas here, the space latent load is only handled, is actually, most of them will be handled by the primary air handling unit. Okay. So for the chilled water system, the fan coil system, the chilled water system for the fan coil unit can be categorized into 2-pipe system, 4-pipe system, and 2-pipe dual temperature fan coil system, related to how the chilled water pipes is arranged. So this slide shows the basic arrangement of the chilled water system. And it's for cooling only. So you can see that we have this chiller connected with a pump, and the pump will supply water, chilled water, into the fan coil unit. And we have one supply, and the chilled water pipes are aligned in parallel with each other, and then we have one major return. So this is called the two-pipe fan coil system, and it's for cooling only. So if heating and cooling are both heating and cooling are considered for the fan coil system, we can arrange the pipes into a 4-pipe system or 1 or 2-pipe system. So for 4-pipe system, basically, first of all, at the fan coil unit, it has a cooling coil and heating coil. It has 2 coils. So it has 2 sets of 2-pipe fan coil system. One set is a pump with a hot water heater or boiler, and another set is a chiller with a pump. So the 2 sets are arranged in parallel with each other, and they are actually individual systems. So the last arrangement of the last type of chilled water piping arrangement is called 2-pipe dual temperature fan coil system. So you can see that for this kind of fan coil system, each fan coil unit only has 1 coil. So this 1 coil can be served as either the heating coil or cooling coil, and it's only related to if the hot water heater or boiler is in use, or the chiller is in use. So you can see that for the source, they are connected in parallel with each other, and then we have a pump supplying water into the coil. So for the major pipes, there is only 2 pipes, or a supply pipe and a return pipe. And the only difference is for the source of the water. So if it's in winter condition, then the chiller will be turned off. So there will not be any chilled water coming out. So this will be turned off. And the boiler will be in use, and it will be supplying hot water to the coil here. And if it's in the summer condition, the boiler will not work. So the flow rate here in this duct is 0. And the chiller will supply chilled water into the system, as here. Okay, so this is all for today's lecture, and I'm going to stop recording.